All right, hi. So welcome back. So today's going to be the last lecture that I'm going to give you. We're going to complete our discussion on the superconducting circuits. Sorry, the door is open. We're going to complete our discussion on superconducting circuits, and on this platform, and then next week you will have the trapped ions platform, and the week after that the atomics platform. Okay, so I hope you enjoy this last lecture that we have together. I will also be present in next week and the week after that, but I'll be audience like you. So let me continue where we left off last time. So last time we started discussing the superconducting qubits platform. We were following this presentation over here. Wait, there we go. Okay. Can everybody see the presentation? Did the share screen work?
Yes.
Okay, great. So let me recap what we did last time quickly in 3 minutes. And then maybe you should ask some questions, clarifications about last time, and then we'll continue. The discussion. Okay, so last time just a second. Okay, so last time we discussed about how these circuits, the idea behind these superconducting circuits is that each circuit is like an artificial atom, and in the same way that in cavity QED, the previous system that we saw, these atoms go into a cavity. Here, these circuits, they're immobile, so they go in a they go in a chip, but they're physically placed in these cavities. But as you take this artificial atom and you place it in a cavity, it forms the same Hamiltonian. Is going to form the same system as a Jaynes-Cummings Hamiltonian, and this is what we're going to see, and we're going to see how that becomes a platform for quantum computation. And we discussed the fact that, just like we have the quantized energy levels, and we pick 2 levels, for example, out of an atom to represent a qubit. For the cavity QED, it was the circular Rydberg states because they had a large dipole moment. Here you would do the same thing with these atoms. And by playing around with these circuit elements, the capacitors and the Joseon junction, which we discussed last time, you can build different kinds of atoms. Okay, so this is and the flow of the whole lecture was that if you take this atom, you put it in the cavity, you can find where to encode your information, either in 2 levels of the atom, or you can even encode it in the levels of the cavity, just like in cavity QED, where you can use the 2 levels of a harmonic oscillator. So you have full control. We can, if we have time at the end, I'll even prove that you have full control for the system, over the whole system, which allows to encode over many levels, the logical qubits. But we'll get to that hopefully at the end. And I gave you these references for reviews if you want to go a little bit deeper into all these things. And we started talking about last time, how to engineer atoms from the circuits. This is the core of the thing, and coupling them to light. We didn't get to coupling them to light, but today we'll get to couple them to light, control, measure how to couple the atoms between them, and hopefully some discussion about how to encode information processing, and how do you see this platform as realizing some quantum computer, maybe. I don't know. So we did this whole circuit quantization. We saw that a simple LC oscillator, a simple LC circuit gives us a harmonic oscillator. We even quantized it, And then we understood that harmonic oscillator plays the same role as light, as a cavity. Okay, so you can have a physical cavity or you can just have an LC oscillator. It plays the same thing. On the quantum level, it's simply light. Okay, we can think of it in electromagnetic mode. And then we discussed the nonlinear element, the Joseon junction, and we stopped right here. I gave you some model for the Joseon junction. And then at the end, I stopped at this, what I called an engineer's equation that shows you that you can regard this Joseon junction simply as a nonlinear inductor. Okay, so this is where we stopped last time. Does anyone have any more questions with respect to what we saw last time?
Just a technical question. Can you upload the presentation to the course website?
Yes.
Okay, thanks.
Yeah. Okay. But you know, don't distribute it. Use it. It's for personal use only. Okay. No.
Okay.
All right. Okay, but yeah, for personal use only, I'll upload the presentation. Yes, no problem. Okay. Also, you have the recording on the videos, so you can always go back to that. But yeah, for convenience, I'll do that. Sorry. Okay, so with this Joseon element, you can start to understand how you take this harmonic oscillator, which is equal level spacings, and you add the circuit element over here, and you now get something that is unharmonic. Okay, so what we're going to do now, we're going to be more explicit about this, because I showed you, okay, I hand waved and I told you, look, you can play around with topologies and get these different energy levels and these different artificial atoms. But what we're going to do is we're going to take an explicit example now, and we're going to discuss one artificial atom, the transmon. The reason we're going to discuss the transmon is, well, the reason you want to discuss the transmon is because it's the most popular qubit there is. It's the easiest to fabricate. It's the easiest to make. It is the qubit that is most ubiquitous. It means it is everywhere. When you're thinking, you know, when you're reading these articles, and when you hear in the news, you know, Google's chip, IBM's quantum computing chip, and so on, they're all based on the transmon. Okay, all of industry and most of the academic groups work with this circuit. The reason is that it is the simplest to fabricate. It has relatively long coherence times, and it is very, very simple to control. Okay, so this is what we're going to see, and we're going to discuss. The second reason why to discuss the transmon is that out of all the qubits, it's also the simplest to explain. So historically it didn't come first, but it is also the simplest to explain. As you will see, it simply forms, and you can see in the energy levels that I've drawn here, it is very, very similar to a harmonic oscillator. It is just slightly unharmonic. And then what you're going to see is that we're going to write the Hamiltonian, and by simple perturbation, you're going to see that you get an unharmonic oscillator. So also in a pedagogical level, it is the simplest one to explain. So that's the reason why we're going to be discussing that. Of course, the first story makes for a nicer story. The second one makes for easier work for me, I guess, for explaining. But there's a lot of rich physics and interesting things to see in other qubits, and I will refer to them as we go along. Okay. Now, this transmon qubit, it's not the first qubit. Historically, it came, maybe if I go back, historically it came as a variation of the Cooper pair box here, or sometimes called the quantronium. If you look at these two circuits over here, these two circuits, the first circuit down here is really the first qubit. It's a Joseon junction with the capacitor in parallel, but this capacitor is tiny. So you want to think about the capacitor, just the self-capacitance of the junction itself. It's a sandwich of a superconducting insulator superconductor, and you can ignore this second Joseon junction. You completely ignore it. So in terms of topology, both the transmon and the Cooper pair box are Joseon junctions shunted by a capacitor. The big difference between the transmon and the Cooper pair box is the transmon has a large capacitor and the Cooper pair box has a small capacitor. But topologically, in terms of the circuit elements, they're the same. Okay? Now, for many years, you can see for a whole decade, this Cooper pair box suffered from short coherence times. And the transmon design, the realization of putting a large capacitor, basically showed that and this is the title of the paper that introduced this type of qubit. It's called charge-insensitive qubit design, because it showed that simply by physically putting an additional large capacitance in parallel to the Joseon junction decreases its sensitivity to charge fluctuations at the expense of unharmonicity. So if you look up here, you can see in the swell over here, we discuss where that comes from, but it basically comes from the cosine potential. You'll see it in a moment. You can see the two levels. And the other levels are far away. So it's a highly unharmonic. It really is very close to a two-level system in that sense. And the transmon comprises that for an increased protection or being insensitive to charge. Okay? I'm not going to go into the details of that. I just wanted to give you some historical context. And you can go into this paper and read it. It is a very thorough, very deep paper. It's a little bit biased in terms of historical perspective, that it starts off with a charge qubit and then explains how you get the transmon. What we're going to do is we're going to straight jump to the transmon, because it's relatively simple to explain. The Hamiltonian, though, for both these circuits is exactly the same. It is what is written down here. So you can see that the circuit is this Joseon junction with a capacitor in parallel. And the circuit, the red part here, this is the capacitor. Okay, so this is the Hamiltonian for the capacitor. It's exactly what we wrote when we quantized the LC circuit. You see EC is just 1 over 2C. Where Q is just, we have E squared, and this is the same Q that we saw previously when we quantized. And here we have the Hamiltonian part of the Joseon junction, where we have EJ cosine phi. This is the energy of the Joseon junction. And what I'm going to do now on the board is I'm going to show you how this forms an unharmonic oscillator. Okay. Is it better if I do unshare screens for you to see the board, or is it the same?
It's the same. We can pin the...
Oh, you can... okay, all right. So I'm moving to the board now. Okay, so the idea you want to think about this, the way you want to think about this circuit is you have a capacitor and a Joseon junction. Okay. And it's very similar to a capacitor and an inductor. Okay, if we go back to this Joseon relation, if you take IC to be, infinitely large, then basically your Joseon junction is just an inductor. Okay, so it looks very much the same. And if I write the Hamiltonian, 1 over 2C Q squared. Actually, let's write it with EC, but it's the same thing. Okay, so let's write it with 4. I just switched because that's like in the presentation. N minus Ng squared. Now, Ng over here, this is just some offset charge. Okay, so if you're putting in a circuit, you can think of a gate voltage that you can put some offset charge. It's not really needed in the transmon because I will show you in a moment, but it's a remnant of the charge qubit. But in the circuit, you can just put a gate voltage. Okay, so, but we can take it to 0 for simplicity. And the second term, this is cosine of phi, which we can write as basically 2 pi over phi naught, and then you have phi, and you might have, phi offset. There might be some offset here. So this is the most general, but we can take phi offset to be 0, and we can take ng to be 0, and it doesn't change it. Now, the important thing, and this is where we enter the so-called Transone regime, this is the assumption. We're going to take the capacitor to be a large capacitor. What this means is that EJ is going to be larger than EC. Okay, this is what is called the Transone regime. Right? No. Now, the important thing about when EJ is larger than EC is that it gives us something very, very nice that we like to do in physics all the time. It allows us to take things that are annoying, like a cosine potential, and develop it in series. What this means is that the 0-point fluctuations, so if I look at the 0-point fluctuations of phi and write them in terms of EJ and EC, you will get this. So it's phi naught over 2 pi. Phi naught is the flux quantum to EC over EJ to the power of a quarter. This is the 0-point fluctuations. And when EJ is larger than EC, then this is much smaller than phi naught over 2 pi. What this means is that the fluctuations here, this phi here, is going to be very small. And this justifies and allows me to develop this Hamiltonian in series now. Okay, if EJ is not larger than EC, then you can't do this because the 0-point fluctuations will just be large, and then the fact that and then this will not be justified. So this is the critical point. And once you do that, then you can. First of all, it's easy to see that this becomes just a regular harmonic oscillator if I take the 0th order, right? If I take cosine and I develop it, the first term is just going to be phi squared. Okay, so first term, okay, so the first term, or first order, we're just going to get H equals, and now I'm going to write, instead of EC, I'm going to write Q, just so it looks exactly like a harmonic oscillator, 1 over 2C, Q squared, plus 1 over 2 LJ, phi squared. Where LJ is just related to EJ over here. Okay, I just wrote it as LJ instead of EJ over here to make it really look like a harmonic oscillator. And from here, it's pretty easy to extract the resonance frequency of this harmonic oscillator. And that's just going to be 1 over square root of LJC, which written in terms of EJ and EC is just going to be 1 over H bar square root EJ times EC, And there's another factor of 8 here, times 8. So to very, very lowest order, this is a harmonic oscillator. The way you can think of it is you have this cosine potential. This is the cosine potential, and this is the harmonic oscillator. So you can think about the levels in the swell over here. Okay, and what we did, we took the first term, so we just took this part over here. Now we're going to take the next term in the series, and in the next term, so the next term we have minus 1 over 24 EJ phi to the fourth. And now I'm just going to write it in terms of our lowering and raising operators. This is the same lowering and raising operators that we saw last time when we quantized. So if I write it in terms of that, so we have phi 0-point fluctuations to the fourth times A plus A dagger to the power of 4. And if I plug this and this in, we get minus 1 over 12 EC A plus A dagger to the fourth. So now we have to take all the terms here in this A plus A dagger to the fourth. But what we're going to do here is we're going to neglect the off-diagonal terms. So all terms that basically do not conserve the number of excitations. So A dagger A we will keep. Okay, A dagger A dagger A doesn't exist, but we're going to have A dagger A, or A dagger A, and so on and so on. Those are going to be the diagonal terms, the conserve. And those are going to be the two types of terms that are going to be here, because all other terms are going to have either 3 A daggers and 1 A, that adds 2 excitations, or 3 A's and 1 A dagger, that removes 2 excitations. And if we do that, then we're going to get minus EC over 2, A dagger, AA, plus 2 A dagger A. Now this here, this term over here, what can we do with it? We can just move it into omega and renormalize the frequency of our qubit. Remember, these A's and A daggers are the raising and lowering operators of our circuit, of our qubit circuit. Okay? So this just renormalizes the qubit frequency, or shifts it a little bit. Think of it as shifting the qubit frequency. So instead of being, if we move to this board, is it moving to this board? So here we had omega is 1 over h bar square root EJ EC times 8. That 2 A dagger A just moves over here, so it's just going to be minus EC. Okay, so the frequency just changes to minus EC. The second term here, this is the unharmonic term. It is the extra energy that we pay for an additional excitation. So if I write the full Hamiltonian, we're going to get h bar omega a dagger a. This is going to be our renormalized frequency. Okay, so omega, and let me write the whole thing, and then minus EC over 2 a dagger AA, where omega now, let's mark it as omega q. Let's call it omega q. Is h bar, sorry, is 1 over h bar, square root of 8 EJ EC minus EC. The factor 2 goes here because you have the A daggers over here. Now, if you plot the energy levels of this thing, so this is a harmonic oscillator. This first energy difference, this is just going to be h bar omega q. So we have 0, this is 1, but now we have 2. The next energy level, the difference between this energy and this energy is just going to be h bar omega q minus EC over h bar. So omega q minus EC over h bar. Where this EC thing, this is called the unharmonicity. So every time you go up another level, the energy difference becomes smaller and smaller. And now you have distinct energy levels. Okay, so do we have any questions about this? About this derivation, how we got to this? Okay, so what I want to pull up quickly, so this is the paper describing what is going on here. It is very thorough. Like I said, I didn't go into all the thoroughness. There's a lot of physics to go. The part which I omitted and alluded to is described about the charge insensitivity is described here. This is the whole part. We did not discuss the charge states at all, and the base is I really did a very rough explanation of what goes on here. But you can actually solve this Hamiltonian. This Hamiltonian here, 2.1. You can see my screen, right? Or are you still stuck on the presentation?
Yeah, we can see it.
Okay. So 2.1, this is the Hamiltonian that we wrote in the beginning. This Hamiltonian can actually be solved exactly for all the regimes, not only for the large capacitor regime. And you can plot the wave functions and the energy levels. This is what you can see in figure 2 for all ratios of EJ and EC. And the Transone regime, the x-axis over here is the sensitivity to charge, basically. It is the offset charge, which is exactly the degree of freedom which we did not discuss. And you can see that in the Transone regime, you're losing this unharmonicity. This is the energy levels that we just quantized and calculated. And if you go to the small capacitor regime, you now have this band dispersion. And the way you work with it is you apply some gate voltage to bring yourself to a regime where you're relatively flat, but you're highly unharmonic. Okay, so if someone wants to read this paper, it is very thorough. It also goes into the details not only of the quantization of the energy levels, but also which level couples to which level. We did not discuss that at all, but you also need to think about how you drive transitions between these levels. Okay, so for example, for the transmon, there is a dipole coupling that leads to a matrix element that will couple every adjacent level to each other, but for example, level 0 will not couple to level 2. So if you can't jump 2 levels at one term. The matrix element over there is 0, and if you want to go into the details of that, you really need to read the paper. Okay, so this is about this paper, but the main point and what I wanted to show you, and the point that I wanted to get across is, well, first of all, is just to give you an example of how you get some unharmonicity and how the Joseon junction contributes to the fact that you can get non-harmonic levels. I do want to add another thing, and that is that with regards to the topology, the topology that I regarded right now is a capacitor that is being shunted by a Joseon junction. It means that the only way that charge can go from one side of the capacitor to the other is by tunneling of Cooper pairs through the junction itself. Okay? And this is the left column over here in this table. If you look further to the right, or even more further to the right, you can see that the Joseon junction is not only shunted by a capacitor, it is also shunted by an inductor, or a set of Joseon junctions. You can think of them as an inductor or a very, very large inductance. And when you do that, first of all, the charge basis is not the most appropriate way of looking at it. And the second thing is that the physics changes substantially. Okay, so there's a whole rich physics to learn there. And I'm not going to go into that, we don't have time, but I just want to mention another famous qubit, the flux qubit. So this is one of the, also one of the oldest qubits, you can see all the way from 2000. And the topology of the flux qubit, you can ignore the capacitor, there's no capacitor here. It looks like a ring with the Joseon junction over here. The large Joseon junction is actually a small one. It has a small EJ. And the smaller ones have a larger EJ. So you can think of them as almost linear inductance. And the states over here for the flux qubits, instead of charge states, are actually circulating current states. Okay, you can see here the red line over here, this is the potential. Okay, so if you remember the original cosine potential, now what happens with the flux qubit is this potential is being altered by the additional phi squared term that comes from the additional Joseon junctions. And if you apply some flux, you can get the two adjacent wells to be at the same level. Okay? And physically, you can think about these two adjacent wells as one well. The state in one well is a circulating current in one direction, and the state in another well is a circulating current in the other direction. And when you bring these two together at degeneracy, there's a tunneling element between the two wells, between these two circulating currents, that causes a splitting. This is the little splitting that is schematically drawn down here. And this little splitting is the qubit that you get. So now instead of thinking of charge state, you're thinking about these circulating current states. Okay? And all this is just coming to say that there's a whole rich world of physics to explore here in terms of topology and in terms of the topology of the circuits and the physics that comes out of it. Okay? If you go even further to shunting junctions, you can add more and more Joseon junctions and go into even more interesting regimes where you can play around with the coupling of these energy levels and suppress some and get some suppressed transitions. And these lead you to more interesting and more recent research works that deal with the topological protection of these qubits. But these are more advanced topics, but there's a whole physics and a whole world of research being explored on this side. Okay, so that's kind of what I wanted to say about that. But going back to our transmon. Okay, so this is us going back to the transmon. Now the transone circuit is designed in such a way that the energy difference between the first two levels is on the order of a few gigahertz. Now a few gigahertz corresponds to a temperature of several hundred millikelvins. Now if you remember the refrigerator where we put the circuit inside gets cooled down to about 10 millikelvin, this is much, much smaller than this energy level difference, and is important because it keeps the qubit most of the time in the ground state, right? We have some thermal distribution, so there is some finite probability for the qubit to be partially excited. Okay.
Question?
Yes.
We only had a difference of EC between these levels, which we assumed is very, very small. So is it enough difference, enough anharmonic to separate between the levels and not to have much noise?
Yeah, well, it's enough to separate, but it does limit, and we're going to see this in not two slides, but in a few slides we're going to see this. It does limit how fast you can do a pulse, because if you want to transition from G to E, you need to give a resonant pulse that is resonant with a G to E transition. But a pulse has a certain, you start it at a certain time and you finish it at a certain time. Okay? You Fourier transform that and you get the spectral width of that pulse. Okay? If it's always easy to think about Gaussians because a Gaussian Fourier transform of that is a Gaussian. So a Gaussian in the time domain will also look like a Gaussian in the spectral domain, and then its width will exactly corresponds to 1 over the time. So if you try to do a really, really fast pulse on the G to E transition, you're going to be hitting the E to F transition, okay, the second level also. And that limits the time which you can do the pulses. So you don't want to be weakly anharmonic, otherwise you're getting closer and closer to a harmonic oscillator, and then you have to do everything slower and slower and slower and slower. So so the point about the transmon, going to the transmon regime, and this was the nice revelation in 2007, is that the suppression of the unharmonicity goes like a power law, while the suppression to the charge noise, that was exponential. So in some regime, and in the regime where your unharmonicity is around 5%, okay, so EC is around 200 megahertz or maybe 300 megahertz, that's 5%, that is a nice sweet regime where you're almost completely insensitive to the charge, and you can do pulses on the order of, tens or hundreds of nanoseconds. We'll see that you can actually do it faster in a moment and mitigate that on these two levels. Okay, so the transmon regime is a regime where you're actually winning in terms of sensitivity without losing too much in terms of how fast you can do the pulses. But this is a very crucial and important point about this design. Okay, so what does it look like? So what you're seeing here, this is a transmon. Okay, so this here, this is a silicon chip. In the middle of the silicon chip is a transmon. This is what you can see over here. The two little aluminum squares that you can see here, this is the zoom in, these form the capacitor. Just two metal bits. They will have a natural capacitance just from the geometry between them. In between them, you can't really see in this picture over here, there's a tiny wire. This is a zoom to the middle of the tiny wire. and you have one aluminum part touching one paddle and the other aluminum part over here touching the other paddle, going to the other paddle. And in the middle, what you can see over here, this is the Joseon junction. Okay, so you have aluminum on the bottom over here. This aluminum is oxidized. So it develops a 1 nanometer thickness of aluminum oxide, and then an additional aluminum is evaporated on top of it, and over here you get your Joseon junction sandwich, which is on the order of 100 nanometers by 100 nanometers. Okay, so this is a Joseon junction, and it is in parallel to these two squares which form the capacitor. So you get a capacitor and a Joseon junction. These two paddles over here not only play the role of a capacitor, but they're also designed in such a way that they form an antenna. Okay? Well, you can see this transmon over here. The chip is placed inside a cavity. This is an aluminum cavity. Aluminum is superconducting, of course. So also the circuit is made out of aluminum. It's superconducting, and this is superconducting. It is placed inside, and in green here, what I've highlighted, this is the first or the lowest lying mode of this cavity. So if you quantize, think about quantizing a box. This is just a quantized box, and you have your lowest lying energy level. That's your harmonic oscillator. The other modes are separated far away. And this antenna here is designed to couple, so it's a dipole coupling to this electromagnetic mode. Was that someone raising their hand? No? Oh, okay. All right. So, so this is what the setup looks like in a complete parallel to an atom in cavity QED going through the field. We have our atom, and it's just sitting there immobile, can't move, can't go anywhere, being coupled to the cavity. It means that our Jaynes-Cummings model, our Hamiltonian, is just going to be on all the time. Okay, our atom is not whooshing through, it's just sitting there inside. And we can send in microwaves through these inserted pins right over here. Okay. What I want to do now is I want to take a quick detour to explain how you do the fabrication. This is for those who don't know. So quick on fabrication and how this is done. To do fabrication, you take a wafer, you coat it with a polymer. This is how, the typical lithography is done. Then you come and you expose the polymer in certain areas, either with UV light, this is called optical lithography, or with an electron beam. You take it into a machine that draws with an electron beam wherever you want, and then you put it in some material that develops it. What the electron beam or the UV light does is they break up the molecules of the polymer, they cross-link them, such that a developer material dissolves them. Okay, so in certain areas where you're drawing, after the developing, you're left with no resist. And this is what you can see as a top view over here. Now the typical situation is that now you put this in a vacuum chamber and you evaporate metal, for example. Then you immerse the whole thing in something that dissolves the whole polymer, and you're left with a pattern basically where everything was exposed. So if I were to do that, I would just get an X over here in this example. But remember, what we wanted for the Joseon junction is we want a sandwich. So we want aluminum, and then we want to oxidize it, and then we want some more aluminum. And we want this all to happen in a clean environment without breaking vacuum, all at one shot in the vacuum chamber. And the way this is done, and this is why you do this like X, there are other ways, but the simplest way to explain is with this X design and what is called angled evaporation. So you take your substrate and you put it in a vacuum chamber. At the bottom of the vacuum chamber, you have your crucible with your metal. And this is the evaporation. Now you evaporate with an angle. And the angle gives the degree of freedom and the key to doing these sandwiches, these extra layer of evaporation. If you evaporate at an angle over here, what will happen if you have a high enough aspect ratio, the metal will go on top. But if you come from this angle, the metal will catch the edge over here of the polymer. But if it's coming from the trench, then it will go into the trench over here. Okay, so on the top view, you can see that you get metal along this line, but nothing along this line because the metal caught onto here. Okay. Now you put just a tiny bit of oxygen into your vacuum chamber to get the 1 nanometer layer of oxide, and then you turn inside everything without breaking vacuum or opening. You turn, so this is the oxidation, make it white, and now you come and evaporate from the other angle, 90 degrees to it. And when you evaporate from 90 degrees to it, you now get, on top of the oxidized strip, you get another strip. And if you make it thick enough, it will kind of climb on top. So eventually you get this superconductor, very thin insulator superconductor sandwich. Okay, and this is how you achieve in fabrication the Joseon junction. Okay, so this is what it looks like. This is how you fabricate the chip itself. Take a 10-minute break, and when we come back from the 10-minute break, we're going to start talking about the system in the context of the Jaynes-Cummings Hamiltonian, see how this forms that. That's going to be pretty easy to follow since we already did that several times, and we did it with QED. And then we'll talk a bit about gates, how to couple the qubits, and the other things. Okay?